All right, welcome everyone. So I will talk in English because Francisco speaks, I don't know actually
Spanish.
if you speak Dutch, but so today we have a very interesting talk by Francisco. But first, as always, I will briefly introduce the Antwerp Young Minds. So we are a group of young scientists, mostly PhD students, and our main goal is to promote physics among physics students, like most of you here, and also physics researchers. And we want to actually provide a widening view of everything that has to do with physics, so not only in your area of expertise. And to achieve this, we organize a number of various activities, so a talk like today, workshops on things that can be of use in your physics career, and also, since last year, also trips to companies or research institutes that have to do with physics. If you want to stay up to date of our activities, then you can find here everything there is to know about our upcoming activities by scanning this QR code. And the QR code on the right gives you some instructions of subscribing to our public calendar. And if you're interested to follow us, you can do that via these channels. And if you have some suggestions for future activities, feel free to contact us. We're always open to have new ideas that we can use for new activities. But for now, I will introduce what we're going to talk about today. So this year is actually marked as the International Year of Quantum Science and Technology. And today's talk is the first event we organize in the theme of quantum to celebrate this year. And so with the Antwerp Young Minds, we want to, for this coming year, provide some extra activities in the quantum theme. For today, we have Francisco, as I already said. A brief introduction. So Francisco studied nanotechnology for his bachelor's in Mexico. And then for his master's, he studied nanoscience and nanotechnology for a combined degree of the KU Leuven and the University of Barcelona. And now he's finishing his PhD here at the University of Antwerp at EMAT. And his topic is exploring adaptive optics in the transmission electron microscope. And nice to know is that actually Francisco will actually defend his PhD thesis this Friday. So he's making some time, especially for us. So I guess that deserves some extra thanks. Then for his main work, it revolves around electrostatic phase plates for electrons, and he will introduce that during the talk of today. And he focuses on exploring adaptive optics in the microscope, which is also the main focus of the talk of today. So I'd like to invite you to give a warm applause to Francisco.
Thanks, Thomas. Yes, this is actually a cool talk and space to practice nervousness before my thesis. Today's talk the idea behind the talk is how to go from basic physics concepts like Young Double Slit Experiment, and you'll see a few other. And often as a physics student, you are like, okay, why am I learning this? Where does it go from this to the actual application? And I tried, and I hope I achieved that, to go from basic physics to what we are doing currently in the microscope there in like the X building in EMAT. So what I want to start with differently than most talks is with a very cool video that we will also check through the talk. So for that, I'll just play it now. Oh, there's no audio, but can I turn the audio on? It doesn't matter. Better with audio, but for today, it's fine. Yeah, so you saw a render, then you saw a lot of bright dots going through something and then reaching black and white moving GIF. But what is it? So to start with, the render you saw is the render of a transmission electron microscope. If you hear microscope in your life and you're not a physics student or anything, maybe you were in high school and you were to the biology lab, and you saw a tool to magnify small objects. And perhaps you can start by saying that the transmission electron microscope is a tool to magnify small objects, but not only that, nowadays, if you check work in transmission electron microscopy, it has become kind of a Swiss Army knife to characterize nanomaterials. And what you can do with this tool is really cool nowadays. You can, yes, have atomically resolved images here, but you can also have different projections by tilting the sample that you're observing and reconstruct nanoparticles down to the atom. You can observe dynamic processes, as you see there, how you take constant pictures of a working reaction as it's working in real conditions in the microscope. On the other side here, you have X-rays that are characteristic of each material. Below, you have energy loss spectroscopy that's also giving you some chemical composition of a sample in the microscope. You can also measure diffraction patterns that are really beautiful, and here, by tilting the sample, you get different diffraction patterns, and they give you information about the structure of your material. But today, what we care about more than these specific beautiful applications is why. And the reason is because in the microscope, we can do wavefront shaping. We can shape the electrons before the sample. We can shape the electron wavefront after the sample. And this gives us a sense of multidimensionality that hopefully by the end of the talk, you'll understand what I mean better. So we all start at the gun. At the gun module, we'll find a tungsten material from which we extract electrons. And those electrons are going to be accelerated towards the optical column in the microscope. And for more specificity, typically, or in the beginning, we started with thermionic emission guns that are more or less similar to what you see in an incandescent bulb, where like a filament is heated up. From that filament, you see light, but you can also get electron emission. But nowadays, we have brighter and better sources in the form of field emission guns. And now what we do is to create a field, and due to the field, we will lower the barrier, the potential barrier of the material, and have tunnel emission to the microscope. But once we get our electrons, we'll take them into the microscope. The first module that we'll find is a condenser module. In the condenser module, you find your first electromagnetic lenses of the microscope. How do these work? By running a current around wires that are like surrounding the aperture, we'll magnetize soft iron pole pieces. And this magnetic field, due to Lorentz force, will create a spiraling effect on a charged particle that's traveling through it, in this case an electron, and it will focus it. Very analogous to what you find in glasses for vision. And by changing this current in the lens, we can change the focal length. And that's important. Here we are shaping the propagation of electrons along the column. Importantly, we'll see briefly, if you flip the current, so instead of running like this, you run it like that, you cannot diverge the beam. You will still converge the beam, and the spiral will just change direction, but you cannot have divergent electromagnetic lenses. But after passing through the condenser module, we get to for some people, the heart of the microscope, which is the objective module, having an upper and lower objective lens, and the sample comes here. So you have your material, you go to the microscope, you insert the holder with your sample, and now the electrons that you shaped before the sample will be scattered there, or not, but a lot of them will be scattered. And then those electrons that were scattered at the sample contain information about the sample. And you can project them with a projector module that also has more electromagnetic lenses onto a detector. And the detector can be simply a pixel that captures all the intensity that lands on this area, all the electrons that deposit their energy on that area, or it can be an array of pixels in a multi-pixel detector. So now we'll get an intensity distribution from the scattered events. And this is as far as like the simplified model that we put together of the microscope, but how do you use it? And the most common way to use this microscope is two ways. CTEM, conventional transmission electron microscopy, is analogous to the biology lab microscope, in which a parallel wave or a plane wave illuminates your sample, as you can see there. And then the electrons that scatter at the sample are collected by a lower objective lens, and they can be focused in the back focal plane of that lens, and give you a diffraction pattern. Or you can create a magnified image if you project them in a conjugate image plane afterwards. Alternatively, what we can do is converge a very sharp probe on a sample, and then we will use coils to scan that probe across that sample. And at each probe position, we can get an intensity recording that's proportional in some way to how the electrons were scattered at that particular site. You can also get an intensity distribution if you measure in a multi-pixel detector. But in the case of STEM, our resolution will be linked largely to the size of this probe. If we can make a very small probe, we can resolve very sharp objects. And to make a small probe, we need to converge it from a larger opening angle. In cameras, it's not exactly the same, but it's a numerical aperture of the camera will give you better resolution. It's analogous in a way. But what we find here is that our lenses are really bad. Any lens, rotationally symmetric electromagnetic lens, will have positive spherical aberration, as it was proven by Scherzer in 1936. And if we look a little bit of math, the first formula today, how do we form a STEM probe? Well, it has to do with the opening angle here, the aperture, but it also has an aberration function. So we want to open the angle more to make a smaller probe, but if we open more, the lenses have aberrations, and the more we open, the worse they are, as it's in this slightly more detailed formula. Importantly, you see here also the opening angle, which will deteriorate, which make aberration worse the more we open. But what is the effect of aberration? And in this very large simplification, what will happen is that the wave will have a different phase of what we expect. And what happens is that the difference in phase, meaning that the wave will have different ups and downs in this sinusoidal case, will create different interference patterns along its way. So there will be destructive interference and constructive interference depending on the phase of this electron wave. But if we place it in a 2D optical diagram, what happens is that what we expect a lens to do, which is just a spherically propagating wave towards a point in the back focal plane of that lens, due to aberrations, will be hindered, and this hindering of the wave will create a disk. So instead of having a point at our sample, we have a relatively larger disk, so we cannot achieve as good resolution as we would like. Yes, and if we plot this aberration function to give you extra evidence of it, you see how if I increase the opening angle, like there in C3, which is called spherical aberration, the phase profile of the aperture that I'm showing as a circle will be steeper and steeper. Fortunately, a lot of people put a lot of effort onto developing an aberration corrector. An aberration corrector is also an electromagnetic lens, but this time, instead of having the optical axis parallel to the propagation of the electrons, the optical axis, the lens axis will be perpendicular to it. And not only that, we'll have several of them. And what these multipolar arrays can do to the electron wave effectively is to break the rotational symmetry of a round lens by orienting it like this, and introduce a small divergence. And a good animation of that is in this beautiful video from Veritasium, I recommend. The electrons will pass through the hexapole. They will be shaped in this kind of triangular way, and it will have effectively a small divergence applied to this propagating wavefront. Then we have a 30 degrees rotated hexapole again, and then we're back to our aberration-free probe, and it continues along the optical axis of the microscope. But going back to where we started, what these aberration correctors effectively also introduce is more multi-dimensionality to the microscope. And all of this is still around the main idea that I want to keep in this talk, which is wavefront shaping. So let's go again through it. Lenses have rotational symmetries. They can apply focus up and down the microscope, but due to the rotational symmetry, they will have aberrations in this case, and they can only focus up and down. Deflectors that we use to scan our probe in STEM, or move our beam in general, have only the capability of applying XY shift to some extent. And aberration correctors are more versatile. They have more multipolar arrays, but it was very difficult to realize this in microscopy. It took 50 years of development since it was known, because the mechanical stabilities needed to keep this thing aligned and in proper shape are very, very precise. On top of that, they can only achieve harmonic phase splits. What I mean by harmonic phase splits is the phase profile in the aperture will be determined entirely by the boundary conditions of these multipoles that you saw. And also they are subjected to high hysteresis. You have magnetic fields, you have ferromagnetic domains around them, and these ferromagnetic domains, due to the field, will change. And that effectively doesn't allow you to precisely apply the same voltage or current to the lens to get the same phase profile. If we take a look at the different field, what happens in optics? They also do wavefront shaping. In optics, they have devices called spatial light modulators, and these devices are very capable of applying position-dependent phase shift to the wave. It means that if you have an array of deformable mirrors, like shown there, there are pixels that are these mirrors, and by changing these mirrors' tilt, you can control the wavefront that passes through it. Liquid crystal displays are another example of this. But effectively, they can achieve position-dependent phase shift, and we can get very beautiful probes like the one shown here. In this case, Hermite and Laguerre-Gaussian modes are called. And this was very revolutionary for light optics. It was a very cool invention that brought a lot of applications to light optics. So now, naturally, we want to go from a spatial light modulator idea and the multidimensionality that we have in the microscope to a spatial electron modulator. Perhaps we can get some applications out of it. For that, we need to focus on the position dependency of the phase shift. But first, let me give you a more easy-to-grasp example, like kind of department physics. Like I'm in my apartment, and I will do a physics experiment. If we have a message behind an object, and we want to decipher that message, if the object refracts the light behind it in a way that we cannot interpret with our eyes, we will not be able to retrieve what's written there. In this case, the object is a transparency with glue droplets that are different size. And it's similar to your shower screen. If you are showering and you have a shower screen in front of you, you don't see anything behind because the light is refracted in all directions, so you cannot make sense of what's behind. However, if we apply position-dependent phase shift, so matching the refractive index of the glue with water, you can see how, despite not being perfect, you now can very clearly read the message with my amazing handwriting behind. And this is because this position-dependent phase shift of the water evens out the refractive index, so now more or less all the waves coming from the hello behind will go in the same direction to your eyes, and you can decipher it. So, despite not being able to control this, but you get the idea, are we going to be able to do this for electrons? Is there any trick? And for that, we need to come up with a recipe, and several ingredients come together between physics and engineering to manufacture this and put it in our microscope. And ingredient number one, title of the talk, is Young Double Slit Experiment. And this comes from the wave-particle duality. If you think about electrons as balls that go through a wall with two slits, without knowing that electrons are waves, spoiler, you'll get some sort of Gaussian profile that has to do with how these slits are positioned. That is not the case. It was originally by Young demonstrated for light, but it's also for electrons. Electrons, in reality, when they pass through a slit, they will create an interference pattern in a screen that records them afterwards. And this interference pattern has to do with the shape of that double slit and the electron wavefront wavelength and some other factors. But effectively, the story here is that electrons are matter waves, so we can take advantage of this and perhaps think for our purpose. In fact, I also showed you that earlier, you just didn't know. Diffraction is a consequence of this effect. If you have a material like a crystal, you can think of these atomic columns as slits through which the electron wave passes. And in this case, as is in 3D, but you can say in 2D, you have all these atomic columns generating a diffraction pattern. And if you tilt the material, you can see how the diffraction pattern changes because we're changing the effective position of those slits. But here, it's really cool, really beautiful data, but we have only position-dependent modulation, but we don't really have an effective way of making this the way we want it. And on top of that, we cannot really control how much the wave will alter its propagation after the crystal. But we have the first one, position dependency. For the second one, we need to look at another physics experiment, and this is the Aharonov-Bohm effect. Aharonov-Bohm effect proved that potential fields are meaningful. In the electrostatic, in this case, Aharonov-Bohm effect, what was stated is that an electron wavefront traveling through two paths, might come familiar already, as it encounters a potential field, careful, it's not an electric field, a potential field along its path. Depending on that potential field, it can suffer an Aharonov-Bohm phase shift. Now, if we place our double slit experiment on top of it, we see the resemblance a bit. And by changing this potential field inside the regions of space, or the slits, we can alter the interference that we will see in a screen later. So here we have control over the wavefront. How do we make this into a device for the microscope? Okay, that's ingredient number 3, the Einzel lens. The Einzel lens is also an electron lens, in this case, electrostatic electron lens, and it effectively focuses the electron. But we don't care about focusing the electron, we care about the phase shift. So to obtain a phase shift, we need to find a way to place a few Einzel lenses along the electron wavefront path trajectory. And by changing the voltage in the Einzel lens, V gamma there, we can perhaps achieve an Aharonov-Bohm effect and control the interference region of the electron wavefront. But for that, we need to miniaturize it. And miniaturization was proposed by Birch in 1947. And as you place a miniaturized Einzel lens after an aperture, you can Aharonov-Bohm phase shift part of the electron wavefront in a way that creates a different interference pattern. So this, again, took many years of development. But after a lot of years of development, Matsumoto and Tonomura in 1996 managed to miniaturize it to put it in a microscope. And now that we have this miniaturized Einzel lens and we know double slit and Aharonov-Bohm, we're ready, right? We have position dependency, we have control over the wavefront, and we have temp compatibility. But one Einzel lens might be not enough. And in Antwerp in 2018, my supervisor and some other collaborators created an array of them, in this case 4. And by using these 4 Einzel lenses, now you can apply voltage to each of them and alter the interference pattern that you will see as the wave propagates. So that's very cool. And so far for the introduction of 36 slides. But let's do a timeline to put ourselves into reference. The Einzel lens, 1926. Then the first microscope was around this time in the 30s by Knoll and Ruska. After that, we moved to the miniaturized Einzel lens proposal. And later on, in parallel, the aberration correction was developed. For reference, I also like to think about myself in time. I was born in 93, so after me, all these things happened. The miniaturized Einzel lens 3 years after by Matsumoto and Tonomura. And from the miniaturized Einzel lens, we put several of them together. Now we have 2x2 control over the wavefront. And now what we have now in the microscope and we can manufacture with relative consistency is wavefront modulation called electrostatic faceplate that contains 48 in the top left or 36 Einzel lenses to modulate the electron wavefront. And this pattern itself is not so relevant, but you can manufacture up to 48 pixels nowadays. And now let's put the physics together to see how much attention you were paying. We start for level 1, where you have a double slit aperture, Aharonov-Bohm effect, Young double slit. And as you start increasing your electrons, you start seeing the interference pattern arising on the screen that you're recording. Level 2, you place 48 slits. And as you start increasing the number of electrons, you see an interference pattern. But in this case, it's slightly different from the other one because the shape of the aperture is different. Level 3, incorporating an Aharonov-Bohm phase shift to one of the slits. And you see how the interference fringes change as the wave function redistributes. And level 4 is just doing the same, but for 48 slits in which you apply 24 with pi, 24 without phase. And you see clearly how this very beautiful diffraction pattern appears. You can change the shape and create different double slit experiments or many slit experiments. You can change the phase and change the wave function due to Aharonov-Bohm effect. So this is very cool. We have it. We have a recipe, we engineer it, and now we can use it in a microscope. If we now compare to what we had in optics, well, you have Hermite-Gaussian modes, Laguerre-Gaussian modes that you see. This is an Hermite-Gaussian mode, this is an Hermite-Gaussian mode, Laguerre-Gaussian modes. We can do it with electrons. And on top of that, we can have control over the actuator or the reconstructor and all these things that are shown in this GIF. And we can do it in real time, as I show you there. So Position-dependent phase shift, we have it. How do we put it in the microscope? Well, you have a brief case of things. You have the faceplate that you put in the microscope, controller computer, voltage sources, cables. What I want to say by this is that if you're a microscopist that doesn't really care about this electron faceplate, you don't really see it. You can use your microscope as normal, and you only have the computer there, another controller here, and the aperture is the same. So it's very easy plug-and-play device that we have for the microscope. And yeah, you can see each device here. But what can we do with this? I told you in the beginning, like, yeah, very basic physics concepts, very ab initio, like demonstrative experiments. But what is the application? How do we link this to what we can use it for? And here we situate ourselves in the microscope, condenser aperture, so the space is very reduced. And typically you have a round aperture in the aperture holder, but now we have our faceplate. And what we'll try to do is to use it for something. And we start from the mid-Gaussian modes and Laguerre-Gaussian modes again. And I will introduce something unexpected, right? Which is the who's who game. What do I want to say by this? When you ask a question, you typically would like to ask the question as efficiently as possible. What does it mean for electron microscopy? If you send an electron to your sample, you will like to get as much information from each electron. If now you send a probe, which is a wave function distributed across your sample, you would like to ask with different probes, perhaps, to obtain different answers each time you're asking. And this is like playing who's who. When you play this game, you try to decipher a character or your sample. And you ask questions. Is your character blonde? Is your character wearing glasses? So by asking these questions with intelligence, you can get to win against your opponent. Well, there's a bit of luck, but you can mathematically win. And we have our different probes, so we have our different questions. Question 1, question 2, question 3. And different questions will perhaps give different answers about the material. And hopefully, we can get to our character by having n equations to solve for m variables. And an example of that, where this comes handy, is for phase retrieval. In phase retrieval, you want to obtain the phase and the amplitude of an object. No need to go on the details on that, but it's often done through an alternating projection algorithm. What this means is that if you have your sample plane with your object here, and you go to the detector plane connecting it with a Fourier transform, you don't directly measure the phase here, but you can iteratively solve for it. And this algorithm is typically known as Gertzberg-Saxton algorithm. The Gertzberg-Saxton algorithm, however, struggles a lot with a thing called the twin problem, which what happens is that the absolute square of the Fourier transform, or the intensity, is the same if the object is like this, or if the object is like this. You can effectively not tell it apart. So when you are trying to iteratively solve for the object, you will be confused between the two, and there's no way of knowing. Moreover, there's a problem with translation. So if you have a very periodic object, like a crystal, and you move a little bit without changing too much the boundary conditions or the field of view, the diffraction pattern is nearly the same. And this also confuses the algorithm. What we can do is to introduce some sort of phase on our wave, so ask questions more efficiently. And by introducing this phase that comes from the Aharonov-Bohm phase shift to our wave, you can see that if we don't introduce phase, hence a flat phase for different doses, you see the twin and the object very clearly in the phase reconstruction. But if we start thinking smartly about which questions to ask to our object, you can see how we can progressively get more information the better questions we ask. What we're doing, we are not asking with more electrons. We are spreading the dose of electrons among different realizations of what we're imaging. So we need to find, of course, that's for another discussion, but best balance between the total dose and the number of configurations that we want to ask. And we also need to assess what happens when we place a real faceplate with a real field factor, so we are blocking part of the electron wave. But this is just to give you some cues into how, using more efficient questions, we can get more efficient phase imaging. But you can also do it for spectroscopy. When you're doing spectroscopy, I showed you an example earlier, but effectively what you measure is how much energy an electron loses to a scattering event on the sample. Now, if our sample has what is called a plasmon, and this plasmon has a symmetry, what is a plasmon? A plasmon is oscillation of the electron C on the surface of a nanoparticle. Maybe I'm not a material scientist, might be a small caveat of that. But effectively, if we have an amount of energy that the electron wave will lose, and we have a plasmon that's symmetrical, for example, here you have a plasmon of a nanorod that's across its surface. It's not the same like this than this. We can use Hermite Gaussian modes in this example to try to obtain symmetric signals for those plasmons when we use our electron beam to sample it. And in fact, we can. And in this study, it was demonstrated how using a 2-lobe beam, a 4-lobe beam, and a normal beam gives different response for those nanoparticle plasmons. So if we optimize the question that we ask, we can optimize the response we get, in this case, from the plasmons. Now, another example in literature is using efficient questions to get efficient answers. In this case, the answer is enhanced X-ray emission for Bremsstrahlung X-rays. If we ask with an unshaped electron probe, like you can see in A, you get an emission profile that's more or less shown as that surface. But if we now shape our electron to match the atomic sites of those emitters, we can enhance that emission. And it was demonstrated through simulations that if we have a probe that's shaped like that, we can have much more emission for the same dose. And moreover, we can even make it directional by shaping the electron further. But what this tells us is we can optimize and have a narrow X-ray emission, which is very important for many applications. What about the adaptive tuning? We covered wavefront shaping, but what can we do with this control loop that is very fast and it doesn't have as much hysteresis as, for instance, an aberration corrector? So we focus on this side of the setup this time. We can have adaptive tuning with this device. So if we have a very simple algorithm in which, from an initial phase configuration and an initial probe or image, as you see in top and bottom, you can get the faceplate or the wavefront shaping device to optimize whatever you are after without any user intervention. So we throw our faceplate, we are looking for a probe, and we want to maximize the intensity of the probe, so most of it is concentrated in the point. And we just run the algorithm, we modify the phase, we acquire a probe image again. Do we improve the goal function? If yes, well, that's our new best. If not, we keep iterating until we're happy. We can also do it for imaging. We put our HADAF detector or any detector to it, we put a goal function, in this case the variance, and as the variance of our image increases, it means that your resolution is also increasing. So we obtain that, not atomic resolution, but automatically improven image. And if we look deeper into why we can do that, is because the faceplate can very well match what a lens can do. If we defocus with a lens, the effect of it will be similar to the focusing with a faceplate. So by doing this rapidly, as a faceplate can update at 100 kilohertz without any user intervention, we can have large acquisition keeping the same optical configuration of the microscope, and the lenses are drifting and so on, but the faceplate can keep them in line to some extent. And finally, to conclude and give some outlook of this technology and this talk, wavefront shaping will provide multidimensionality to the already multidimensional TEM. And if TM is a Swiss Army knife due to this multidimensionality, perhaps adding more will enhance its capabilities. And yes, I show you this with these examples. Moreover, if we harness quantum physics concepts and experiments of the past in a smart way, in a creative way, we can develop a tool that's capable of being used for state-of-the-art electron microscopy and materials characterization. But when it comes more to the faceplate side of things, I showed you how position-dependent phase shift, increased multidimensionalities, you have new possibilities. Moreover, you can shape the electron wavefront very fast and without user intervention, and perhaps that allows you to have more and more creative schemes to come to the microscope. And the roadmap, in the historical part of it, we saw how we started from an idea, and then it materialized to the miniaturized Einzellens, for instance. Then we have the first design for proof of concept. Now we are here with a 48 pixel. And what is to come, engineering needs to match physics and theory in order to keep the wave of motivation going. If we have a good theory, then we can follow with engineering. And then good engineering makes people to adopt the technology and have even more theories and start putting more creative output. And with that, I want to thank everyone, Antwerp Young Minds, some funding institutions that I need to mention, I think. And of course, Gert for the video that you already know what it means completely. And thank you for your attention and welcome any questions.
Does anyone have a question? Perhaps? Yeah?
So you mentioned from the introduction of the miniaturized Einzel-lens to the array of Einzel-lenses. It was quite some time. So what was like the big challenge from going from a single lens to an array of them?
I think the miniaturization of the technology, I think it comes from like these lithography techniques and multi-layer techniques to miniaturize it. In 47, if you read the paper from Bosch, he writes like, yeah, this could be very cool. He proposed it for those who are biologists to bring Cernicke phase contrast, which was a Nobel Prize winning thing in optics, to bring it to electron microscopy, because we also put biological samples there. In terms of the technology, I don't know precisely, but I would assume that in the 50s we just didn't have the miniaturized technology to do those things like these lithography processes and so on. So I suspect it's on those directions. Yeah.
If you have to interrogate and ask the best questions, then you can use information theory.
Yes.
Did you try?
Yes, indeed. That's our most recent paper with Jo, but I didn't want to cover that because maybe it was going to be a little bit too theoretical. But information theory, to those who are a bit more aware, goes more into the details of how we form the image and how we transfer frequencies to it. And what they say is the best is to use random distribution of phase, and then spread the configurations, have different configurations spreading the dose. But in the end, you will need to quantify with Fisher information, Kramer lower bound, and all these things. Effectively, in that paper that we published, we just want to know how much information is in one electron. And it's kind of like a very meticulous derivation for it, but information theory is the only way to do this asking efficiently. I just mentioned it on the surface to make it like as general audience, but yeah, you need to have the model, the forward model of all this and scattering and so on.
Any other questions?
Yeah.
Yeah.
Tonomura proved this at Aharonov-Bohm
Yes.
in 86 in the Kyoto conference.
Yes, but before that, it was the Davis and Germer experiment with the diffraction, or it was very close together, I think. Yeah, Tonomura did the holography, and he moreover proved that one electron interferes with itself, not many electrons. Yeah.
Yes. Yeah, Matthew.
I was wondering, like, at some point, I think it was slide 29, where you mentioned that you were, that you could choose basically the sizes of your diffraction slits with the spaces between the atoms. I was wondering how does that work in practice the way I think it does? Like you choose a certain material that has a crystal structure with the atoms in that position, or is it something else? Like, do you engineer it?
I'm a very bad material scientist, but yeah, of course, like if imagine you're the best, imagine you have like a 3D printer of crystals. If you have a 3D printer of crystals, you can just put atom after atom and create this crystal. And I guess that in this very hyperbolic argument, you can just change the spacing and change the from gold to silver and so on, and that will give you a lot of control. But like, yeah, that's. But yeah, if you change that.
Is that what you do in practice, or is that what?
No, I think that's like, for instance, like Saleder, like this is his data. They have all these structures in his group where they have like beautiful diffraction patterns from MOFs and some other materials, but it's more the other way around. They have the diffraction pattern and they want to guess the material because they typically don't really know what's there. And defects and all this, more complicated. Like we went the long way doing Einzel lenses and all of that.
Yeah.
Since this is a quantum physics talk, I want to emphasize that your discussion about the opening angle, large opening angle, small spots, that's Heisenberg.
Yes.
Opening angle is inserted on the wavevector and the spot is on circular position.
Yes.
So you directly see Heisenberg in the microscope.
Yes, I missed that one.
So you can directly Fourier transform in the microscope.
Yes, indeed. So it is indeed, as Dirk says, Heisenberg, and I missed that. But the wavelength of the electrons is also important. That's why I showed you that we accelerate them very fast. The faster they go, the shorter its wavelength. And the shorter its wavelength, the smallest thing we can resolve as well. But I omitted that a bit. But yes, and it also has implications for.
That's why a microscopy is much more interesting for physicists than for biologists, because we can think in really Fourier space once and back. Descartes.
Was there also a question in the back there? Perhaps a question from the students? Okay, then perhaps I will ask a question. If there's a lot of students present here. If there's one takeaway that you find the most interesting physics-wise to give to the students, what would it be?
More than takeaway, I think when I was writing my thesis, I found a quote by Fritz Zernike. This sounds like very cheesy, but bear with me. He to some extent, he said like that he was surprised how easy it is to understand what someone else puts on a slide and how easy it is to understand the equations and so on, but how hard it is to understand the fundamental principle behind everything that's happening. And that's not even through PhD you get it. You need to really grind it through and to physically understand what's going on. Because equation and slides and what you showed, we can get to it, but the depth of it, it's way more difficult. That's a cheesy takeaway. A cool takeaway is it's fun to do these things. You can just try, and there's a lot of openings and positions.
We think in terms of electrons. There are always waves until they hit the detector. Only then we'll see electrons. You never see electrons inside. So the whole quantum mechanics is wave mechanics up to the detection. It's very important to get that.
Okay. Any last question that pops up now? Then let's thank. Okay.
I'm just curious, just about specifically your thesis, about what you did, and well, more specifically, maybe did you do theory of it, or was the theory actually already done?
This is how real science works, I guess. The little things I know. So my thesis, I got like an interview with Jo, and he said, yeah, we have this faceplate. I didn't know what it was at all. I barely knew what microscopy was. And it's often a problem between engineering and physics. So through my thesis and through most PhD theses, things don't go as planned. So I had a faceplate, and when I had a faceplate, I took the data, so I was experimentalist. But for a very large extent of it, I tried to conceptualize it in an engineering way as well. We design a faceplate, so theory, how to design a faceplate. We characterize a faceplate. So we have a device, how do we use it, and that's engineering. So theory, engineering. And finally, as the faceplate sort of broke, and we don't had one in the microscope at the time, we moved on to what Dirk was saying, like information theory. So how do we ask questions the most efficiently? But it's more about adapting through the PhD. I cannot say that this will be the truth for many PhDs. At least my topic remained the same. Some PhDs completely changed. But you can always find, and I think for my case it worked the best, to balance engineering, theory, going to the microscope, not going to the microscope, and so on.
Thanks.
Okay, then let's thank Francisco once again. I've been told that he likes beer, so some of them also some gifts for you. And thank you very much for taking the time to give us some interesting talk. And if you have any more questions, we now have a reception outside for some snacks and drinks, and you can bother Francisco with all your silly questions or interesting questions that you might still have.
That was not agreed upon, eh? No, it's fine.